Hey, everybody. All right. Whoa. All right. It's 5:30, so let's go ahead and get started today. All right. Good evening, everyone. How's everyone doing today?
Doing really well. How are you? You look
Good.
sleepy.
I am sleepy. It's definitely that time of the semester when things get crazy, but hanging in there. Yeah, I've been telling all my classes that it really it feels which is which is kind of just a hunch from my end, but it feels like this semester the energy level is just kind of way down compared to usual. And the reason is because we've been stuck inside for so long, right? And so like at least for myself, I feel like yes, it's the end of the semester, you're always going to be tired, but I think beyond just that, I think it's just really fatigued just from all the time that we've been spending in this pandemic. Because for the past year, I mean, you guys have been taking these classes virtually, and like that's you know I think I think when we first went into this, maybe people didn't think it was that big a deal. um, but if you think about it, your entire life is being spent in front of your computer now, right? Like you do, all your school in front of the computer. You're relaxing in front of your computer too, right? And school has really entered the home, which I think is an effect that a lot of people take for granted, because now there's really like no escape, because I think before, when you went to school or you went to the office, there was like a physical separation of, I did my work there and I do my relaxing here. Now it's all in one place, and so now, you really, at least for me, I feel like I don't really get the same amount of rest, because, it feels like, my work is right there, just like kind of staring at me, just, waiting for me to do it. So, it's tiring, and, I just want to say that I feel it for you guys. And, as hard as it is, teaching during this time, I think, it's probably twice or three times as hard to be a student during this time. So, just want to say that, I feel for you guys, and, just, hoping that we can get back to normal sometime soon, because this is I mean, we do our best, but it's definitely not the same kind of experience as you would get in person.
Have you received any news that we're going back into the fall at all? Because I was registering and I see some of the rooms being like 309. Have you received any faculty word of us going back at all, or?
Yeah, so the latest news from the provost is that they're aiming for the number that they have is 65% back, and so they're aiming to have about 65% of the classes back on campus in the fall. And so, I mean, priority for that is going to go towards the lab classes, which I think benefit the most from being in person. But they're still going to offer some courses virtually. At least that's what I understand. But they also are requiring all the faculty to be on campus during the next semester too. And so, at the very least, I won't be able to work from home next semester. I have to go, even if all the classes that I teach are virtual. But that's the latest news. That's the latest number. In terms of planning, I don't know what the status of that is, because it's going to be department by department. But they're aiming for 65% of classes back in person in the fall.
Okay, gotcha.
Yeah.
Wonder where we'll park because they're building a new structure, but
Yeah, I drive by that too, and they're busting out the crane. It's funny because they spent the last year before that building that new parking structure, but now they raised a big parking lots, and so now our net gain of parking spaces might be zero, which is kind of funny. Okay, and so just like I promised you last week, we're not going to talk about any kind of difficult partial differential equations or any kind of graduate level math anymore. And so, we're moving back to kind of the more kind of conceptual stuff. Okay. And so we're really kind of in the late stages of this class. And so, at this point, a lot of the topics that I have left are kind of more, I mean, they're important topics, but they're more kind of miscellaneous compared to kind of the main topics of this class. And so, for this week, we're going to talk about kind of the two parts of the circulation that we haven't talked about before, which are the veins and the microcirculation. And then next week, I actually have a talk. I have a lecture planned on experimental methods. Okay, so even though most of this class is on computational modeling, I think it's important to talk at least about some of the experimental methods that are done as well. Because especially, if a lot of you guys are going to go and work for, like Edward Life Science or Medtronic, they're using a lot of the methods that we're going to talk about next week. Because I've seen it. I've been to the Edwards campus and I've seen I've seen them use a lot of these methods. And so, hopefully that will be, interesting for you to look at as well. Okay. Next Thursday is our midterm. And so I sent an email about that to you guys today. And so I have a study guide posted, where to help you study. And on this Friday, I'm going to do a kind of like a review video, kind of like what I did for the last midterm as well. Okay. And so keep an eye out for the poll. So I think I'll probably post the poll on Thursday. And the plan is to cover everything for the midterm, to cover basically everything since the first midterm up until this week. Okay. And so the lecture notes that I have on microcirculation, that I do plan on that being on the midterm. Okay. So make sure you study all of that stuff. Okay. And in terms of the format for the exam, I know we talked last week about, having this be an all conceptual exam. And so I am going to do that. And so instead of having, kind of like what I've done before in the past, like kind of half conceptual questions, half problem solving, this one's going to be all conceptual questions, just because, nothing that we've done since the first midterm is kind of conducive to like a good kind of hand calculation problem. And I haven't asked you to do any homeworks on that either. And so, I think it's only fair that I only asked you stuff on conceptual questions. Okay. And so in total, there's going to be 8 conceptual questions that I'm going to ask you on the exam. And just like before, you would just type the response into the browser. Okay. Okay. All right. So that's all the announcements that I had. And so are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. And so the topic for today is what I call venous biomechanics. Okay? And so these are going to be the biomechanics for all the veins in your body. Right? All right, and so here's the learning objectives. So first, we're just going to discuss, what are just the general roles that veins play in your system. Okay, and we'll define some important physics that they have, especially compared to the arterial system, as well as some interesting mechanics like the calf muscle pump and the respiratory pump. Okay, and so let's kind of remind ourselves what the veins actually do, because I think we talked about it at the very beginning of the class, but we kind of ignored them up to this point. Okay, because for most of this class, we've really spent all our time just focusing on the arterial biomechanics. Okay, and so remember, the arteries are the blood vessels in your body that carry blood away from your heart. Okay, and so these are blood vessels like your aorta, like your coronary arteries, like your the arteries in your brain, right? Some of you are doing for your project. Okay, and so generally, arteries are of higher clinical interest and engineering interests, just because these arteries have a lot more. They have much higher pressures. They have much higher flows, and they're usually most cardiovascular diseases, they affect your arteries. Okay? And so, for most cases, and you'll see this in textbooks too, most of the focus is usually spent on the arterial system. Okay, and that's kind of what we've been doing in this class. But that's not to say that the other parts of your circulation are important. And so for today, we're going to focus on the veins. Okay, and so the veins serve the important purpose of collection. Okay, and so after the arteries carry the blood away from your heart. And remember, when it carries the blood away, typically this blood is rich with oxygen and rich with nutrients. Okay. And then once this blood reaches your important tissues, like your organs and your muscles, then that's when it gives up all of its oxygen and materials. But then after it does that, then the blood needs to return back to your heart. Because remember, your cardiovascular system is a closed circuit. Okay. And so the purpose that the veins serve is, they're tasked with collecting the blood after it passes through all of your organs and muscles, and then bringing that back to the heart. Okay. All right. And so one big important property for the veins is that they actually store a very large percentage of your blood. So about 60 to 80% of the total blood volume is actually stored within the veins at any given time. Okay. They have much lower pressures. Okay. And so the veins, arteries are typically operating in pressures of like 80 millimeters of mercury, 120 millimeters of mercury. And the veins, these typically operate anywhere between like 5 and 7 millimeters of mercury. And so you're talking about like an order of magnitude less for your veins. And so, that's a big difference. And the flow in your veins is actually relatively constant as well. Okay. And so, we've talked about in the arterial system where your blood flow goes up and down. Okay. So we've described that as pulsatile. And so in the veins, you don't have that. In the veins, you have relatively constant flow kind of all throughout the veins. Okay. All right. And so, because the pressures are so low in the veins, What you'll see later is that your posture actually strongly affects, the venous flow. Okay. And we'll see, that, the main reason is basically just hydrostatic pressure. Okay. And, even though there's not as many, but venous diseases can have, can be a big concern for people as well, right? And so you might have heard of some diseases like varicose veins, or we'll talk about another serious one here called deep vein thrombosis. Okay, and so these can be, a serious concern, and because the venous system is relatively, less studied, there's a lot less that's known about these venous diseases than the arterial ones. Okay. Okay. And so that's just a general introduction of the venous system and kind of where we're going with these with this lecture slides. Right? So any questions on any of this so far? Okay. Okay. And so first, let's talk about the composition of the venous vessel walls and this idea of compliance. Okay. And so just like the arterial system, your veins are these kind of flexible tubes. Okay. And so the way that we talk about them is we call them compliant. Okay. The amount of compliance or the amount of flexibility, these depend on things like geometry, material properties, influence of the surrounding tissue, as well as this new kind of parameter that we're dealing with in veins called the transmural pressure. Okay, and so all transmural pressure is basically just a difference in pressure between the inside of the vessel and out. Okay, and so the formula for transmural pressure is very simple. And so you just take the internal pressure and then you subtract it from the external pressure. And so that's how you get transmural. And so, I'm introducing this as a new concept, but, it's not like this is absent from the arterial system, right? And so for the arterial system, you have transmural pressure as well, because, a lot of blood vessels in your body, both your arteries and your veins, they're surrounded by tissue around it, right? And so you have blood vessels that run through your muscles, you have blood vessels that run through some other, soft tissue in your body, okay? And so that tissue, it's going to exert some force on your blood vessels, okay? And so it's going to squeeze it a little bit. And so that's where the external pressure comes from, right? And so that's true of arteries and veins. But for the arteries, we kind of ignored it because, remember, for the arteries, they have a much higher internal pressure, okay? And so for the arteries, because their internal pressure is so high, we can often ignore the effect of the external pressure because it usually doesn't have that much of an impact, okay? But for the veins, remember, our internal pressures are a lot lower. Now, all of a sudden, this external pressure that we get from the surrounding tissue, that's going to play a big role on the venous behavior. Okay, and so when we talk a lot about vein biomechanics, this transmural pressure is something that's really important. Okay. All right, and so if you compare, directly a vein and like an artery from around the same part of the body, usually your veins are going to have thinner walls and larger diameters, and so this allows the veins to deform a lot more easily compared to its arterial counterparts. Okay. Okay. So any questions on this so far? Okay. All right. And so let's talk about an important behavior that veins do, and that's collapse. Okay. And so since veins have a higher compliance and because their internal pressures are a lot lower, the walls of your vein can actually collapse, right? So visually, it actually looks something like this, right? And so visually, you have your vein, then, we're going to assume that it starts as a perfect circle, but as the external pressure starts to exceed the internal one, it literally starts to be squeezed. And so you can kind of think of almost like a rubber band or like a stretchy hairband, right? And so if you take that band and you kind of squeeze it with your hands, eventually you can kind of deform it into this kind of like dumbbell looking shape that you have right here. Okay. And that's something that can happen to veins because their internal pressures are so low. Okay. And so as you can imagine, collapse will only happen when the transmural pressure becomes negative. Okay. And so in other words, the external pressure is higher than the internal one, right? And so, there's been a lot of work out there that kind of is out there to model this effect of vein collapse, right? But this is kind of one of the more simpler models. Okay? And so if you assume the vein is basically the same as like a thin-walled cylinder, like a thin wall structure, okay, from your structural mechanics class. And so if you kind of work through the math and you work through the derivation, you can come up with this following formula to predict when the vein will collapse and start forming non-circular cross sections. Okay. And so if the transmural pressure, and this is negative transmural pressure because we have P external and minus P internal, if this is equal to E times H cubed divided by 4R cubed times 1 minus nu squared, okay? Then if the transmural pressure gets to this point, then you're going to start to have vein collapse, right? And so if we define the various parameters in this expression, the E here is the Young's modulus, the H here is the wall thickness, big R here is the vessel radius, and nu here is the Poisson's ratio. Okay, and so once the transmural pressure exceeds this number, and so you plug in all the numbers for this, you get something in the units of pressure. Okay, and so once the transmural pressure exceeds this number, that's when you start to have this kind of vein collapse behavior. Okay, right? And of course, if you do things like if you squeeze your hand, or you apply pressure to your veins, that also encourages this vein collapse. Okay, because this external pressure that we see here. You can also kind of externally apply that as well. Okay, so if you squeeze your arm, you squeeze your wrist, right? And so I think a term that people are familiar with is like if you kind of squeeze your wrist really hard and you do that for an extended period of time, you cut off the circulation. Okay, and so what's likely happening during those times that you're increasing this external pressure and you're causing your veins to collapse under that pressure. Okay. And so, this venous collapse, happens naturally all the time in your body, but you can also encourage it to happen by kind of squeezing, the veins yourself externally. Okay. All right. So any questions on this so far?
Professor, I think there are a couple questions in the comments.
Oh, sorry. So I was in presentation mode, so I didn't see the chat. Yeah.
Yeah.
All right. Oh, question. So let's see. Oh, wow. There's a lot of questions. Sorry about that, guys. Right. Yes. Yeah, it kind of sucks to graduate this semester. I feel you, Ronald. Yeah. Yeah, I think I saw an email recently that they are going to require vaccinations to attend in-person classes. I don't know what this. I think they kind of just announced that. I don't know what their plan for that is exactly. Yeah. All right. So after the midterm, there's going to be actually after the midterm we only have 2 more class sessions. And so for one of those, I'm actually trying to organize. I'm trying to get a guest speaker. And so I have a good friend that actually works at a biotech company called HeartFlow that actually does computational simulations for their professional work. And so he did say that he's down to give a talk, but I need to kind of confirm with him to make sure. And so that's going to be one class session after the midterm, and then for the other one, we'll see. Well, I'll figure something out for that one. The midterm will just be in class, and so it won't be a week-long midterm, and so it'll be just a 90-minute midterm that you do in class. Yeah. All right. So is there any type of air in the vein, or is it under a vacuum? So the vein is filled with blood, and so there's blood that fills the vein. It's just at a much lower pressure. Yeah. It might seem like it's air because the internal pressure is a lot lower, but there is blood inside the vein. Do you have to show up for the midterm? No, you don't. And so if you want to just take the midterm within the piece of your own apartment, that's fine too. Yep. And there's no final exam. And so remember, there's only the final project for this class. And so once we're done with the exam next week, that's it for exams for this class. Won't air in your veins kill you? So it's not good, and so it's because your blood flow is a closed circulation. Like if you have an air bubble that shows up in your blood vessels, there's really no way for it to escape because you have a closed circulation. And so the concern is that if you have an air bubble, and it becomes really big and the blood can't pass it and it kind of gets stuck, that's bad. But usually for that to happen, some medical procedure has to go wrong. And so that doesn't happen all too often unless you take an empty syringe and you push it into your body, then that's likely not to happen. Yeah. Okay. Yeah. So sorry about that. Oh, go ahead.
Sorry, I was the one that asked how long the midterm would be, like if it was a week long, or if it was like for the whole class.
Yeah.
Could you was the answer for the whole class?
Yeah. It's just a 90-minute midterm, and so it's just going to be in class. Yeah.
Okay, thank you.
Yep. Mm-hmm. Yeah. Oh, I meant more for the time slot for the final. Oh yeah, no. Yeah. So I know this class has a time slot for the final, but since we're not taking a final exam, you know, you don't have to show up. I won't be there. And so, you know, if you guys want to show up and have a party yourself, that's fine. But, you know, I'm probably not going to be there. Yeah. Okay. So I'll keep the chat. I'll keep the window minimized like this, you know, just so I can see the chat. Cause I think when I'm in presentation mode, then I can't see it. So let me see, is there a way to view this without the side? Let's try reading view. Okay, all right, so this is much better. Now I can see the chat. Okay, and so that's the behavior of venous collapse. And now let's talk a bit about the pressure area response of the veins. Okay. And so, you know, because the veins have this ability to collapse on itself, kind of the relationship between transmural pressure and the cross-sectional area is something that's really important. Okay, and this is another thing where, you know, people have been trying to model this for you know, for many years now, and there's a lot of models out there, some a lot more complicated than others, but this is kind of one of the more simple ones that I've found. And so this is kind of what they call a tube law, which kind of shows this kind of direct relationship between, you know, the transmural pressure and the cross-sectional area. And so A here is the is kind of the current cross-sectional area, and A naught is kind of like a reference area. Okay, and so if you follow this equation right here, this will give you kind of the approximate you know, pressure area relationship for the curve or for the vein. Okay, and so basically what this is saying is that, you know, as we increase the transmural pressure, or as we increase the external pressure, then the cross-sectional area is going to go down and down because the vein is collapsing on itself. Okay, so that's all this equation here kind of represents. Okay? Where this Kp here is known as the bending stiffness of the model, and you can compute it from this you know, from this equation here. Okay? And so if you plot out the this pressure area relationship, it kind of looks like this. Okay, and so this plot here is a little bit hard to understand. So let me go ahead and kind of explain what's going on. And so right away, what you see here on the y-axis here is these are the transmural pressures, and you can see here that we're only considering negative transmural pressures. Okay, and so this is for the case when the external pressure is higher than the internal one. Okay, and so you can see here that we have this section of the graph, and so actually the best way to read this graph is going to be from right to left, strangely enough. Okay, and the reason for that is, you know, I basically want to show you what happens as you decrease that transmural pressure, or as that external pressure goes as that external pressure goes up and up. Okay? And so you can see here that, you know, for this region of the curve right here, for just a small change in the transmural pressure, and so you can see here that the transmural pressure goes from maybe -4 down to like -4.5, or -4 to -5. You can see here that we have a huge reduction in area, right? And so we go from maybe here down to like over here. Okay, and you know, during this time right here where the curve is mostly flat, this is when the vein is collapsing, right? And so we're going from a full kind of full circle, you know, and as we increase that external pressure, then that circle's going to squeeze until it gets to the point where you have contact. Okay, and so once you have contact, so once the two ends of the walls kind of meet, then the cross-sectional area from there doesn't really change much at all. Okay, and so you can see here that once we reach kind of this vertical section of the graph, that if we increase this transmural pressure, or we decrease it more and more, then we don't see nearly as much change in cross-sectional area. Okay, and so the parts that I want to highlight for you on this graph are, you know, here on this flat part, this is basically where we have collapse, and then once the vessel is fully collapsed, then it takes a much higher pressure in order to reduce the area even more. Okay. Okay. So any questions on this so far? Okay. All right. All right. So now let's talk about the blood flow. And so now, now that we've talked about this idea of vein collapse, now we're ready to talk about, you know, what is the how does the blood flow, or how does collapse affect the blood flow in the veins? Okay. All right. And so we see from here that, you know, as the vein collapses, the cross-sectional area of the vein is going to go down very rapidly. Okay. And we know from our previous weeks or previous lessons that, you know, as the cross-sectional area, or as the radius of the vessel goes down, then the flow resistance is going to go up, right? And so if you remember, you know, we have this expression for the resistance here, where resistance is equal to 8 mu times L divided by pi times radius to the 4th, okay? And so as the vessel gets smaller and smaller, then this resistance is going to go up and up, okay? And so you can see vein collapse is not something that you want to sustain for a long period of time, because if you have vein collapse and it's happening for over a long time, that means your heart is going to need to work harder and harder and harder in order to push blood flow through your body, because the viscous resistance is going up and up, okay? And so that's why you don't want to walk around with like rubber bands around your wrist, because it's going to cut off circulation to your hand, and your heart's going to have to work harder and harder and harder in order to push blood through that. Okay, and so that's typically what you don't want to do in those cases. All right, and so another thing that's important to know is that as the cross-sectional area decreases, then the fluid velocity is going to increase sharply as well, due to conservation of mass. Okay, and actually, the blood flow can be accelerated so much that it can match the wave propagation speed. And this actually results in supercritical flow in the veins. Okay, and so here's kind of an example of what can happen. Okay, and so as the vein kind of collapses, and so this is actually another figure from something else, but I thought it kind of illustrated this really well, where you have flow that's coming in through this kind of tight area right here, and it's causing a very large increase in velocity. Okay, and so and so because the veins can collapse to almost nothing, you have this kind of unique problem in the veins where the veins can almost act like almost like a rocket ship nozzle, right? And so if you're kind of familiar with aerospace, then you're probably familiar with this idea of supercritical flow, where if you converge airflow enough, then the speeds in that nozzle can approach the speed of sound. Okay. And that's typically how you achieve kind of maximum propulsion in those kinds of systems. And so in veins, you can achieve kind of a similar phenomenon. So you're not going to accelerate your blood to the speed of sound. That would be kind of crazy. But what can happen is that, because the veins can collapse so much, you can accelerate the flow enough such that the blood flow velocity matches the wave propagation speed, right? Because remember what we talked about before, that the pressure waves are basically riding along these blood vessels. And usually what they do is they ride along at speeds that are much higher than the blood velocity, right? But for the veins, because they can collapse so much, you might get situations where the blood flow velocity can match the wave propagation speed. And when that happens, you get what's known as supercritical flow in your veins, right? And so that's something that's kind of unique to to vein flow. Okay. So any questions on this so far? It sounds like a cool power up. Yeah. And so I'll say this too. And so all this stuff about the veins, I've actually never studied them either before too. And so all my previous work has been on arterial flows. And so when I was producing these lecture slides, I was kind of learning a lot of this stuff for the first time as well. And so a lot of this stuff's like, wow, that sounds really cool. And so the textbook mentions that you can get supercritical flow in your veins, but I don't actually know if that's like a or if that's like a bad thing, or like if that leads to anything bad for the person. And the textbook was a little bit vague on that. And so that's something that I'd actually be interested in studying a bit more, because it seems like it's a really interesting thing. Yep. All right, question. So what causes a collapsed vein? So a collapsed vein is kind of what we were talking about earlier. When you have, basically what happens is when you have the pressures around the vein, when those get higher than the internal pressures, then the vein kind of collapses in on itself, and you get kind of these kind of weird dumbbell looking shapes, right? And so what we talked about before was that this is really relevant for veins, because the internal pressure in the veins, or the pressure of the blood inside, is very, very low compared to the arterial ones, right? And so if you squeeze a vein, it's very likely that you can collapse it because the internal pressures are so low. But if you try to do that for an artery, an artery is very highly pressured, and so it takes a lot of squeezing for you in order to kind of collapse an artery, because the pressures inside are so high. But veins have such low internal pressures that you don't really have to do much to squeeze it, and you can get a collapsed vein like this. Yeah. Mm-hmm. Yeah. So one thing you can do, and don't try this for any extended periods of time, because it's a health risk. But if you take a rubber band and you tie it tightly around your wrist, then people kind of think of that as like you're cutting off your circulation. But what you're actually doing is you're cutting off you're collapsing all the veins in your hand, and so basically the blood can't escape from your hand, because there's no way for the blood to kind of escape from the veins. Right? And so you're not actually collapsing the arteries in your hand when you cut off your circulation. What you're actually doing is you're collapsing the veins, and so blood actually will start to pool in your hands, and that's why your hands get kind of numb and kind of like purple because the blood is kind of pooling up there. Yeah. Okay. And so that's a lot of the fluid mechanics and kind of the wall mechanics of veins. And so now let's talk about some clinical parameters. And so the main clinical parameters that doctors look at when they're assessing the health of your veins is this thing called venous return. Right? And so venous return, what this is it's a clinical parameter that basically defines the volume of blood that returns to your heart from the veins. Okay. Right. And so if you look at kind of this very simplified version of the heart cycle here, basically what you have here is, let's start from the left ventricle, because the left ventricle is the chamber of your heart that pumps blood to most of your body. Okay. And so when your blood leaves the left ventricle, we call that your cardiac output. And so the cardiac output is basically a measure of how much blood your heart is pumping out in each heartbeat, right? And so the cardiac output is the amount of blood that goes out. Okay. After the blood goes through your systemic circulation, then your systemic circulation being things like your organs and your muscles. Okay, then the blood has to return to your heart, where it goes into your right ventricle. Okay, so that's what RV stands for. And so the amount of blood that returns to your heart from the rest of your body is called the venous return. Okay. And so as you can imagine, you need to maintain, your body needs to maintain a healthy amount of venous return, basically to ensure that your heart has a continuous supply of blood. Okay. Because if the blood's not returning to your lungs, then there's no blood for your heart to pump out, right? Because your cardiovascular system is a closed circuit, right? And so there's a finite amount of blood, that's inside your body at any given time. So your body can produce more blood, but it goes at such a small rate that basically, your heart, wants to be circulating that same blood. Right? And so you want to make sure that your venous return here is a good, healthy amount, such that your heart can kind of oxygenate that blood and then pump it back to the rest of your body. Okay. And so when doctors are assessing your venous health, they're looking at this venous return as a way to assess that. Okay. Right. And so you can think of it as almost like not really, I guess the inverse is not really a good word here, but think of it as the opposite of cardiac output. Okay. Because cardiac output, remember, is a measure of the amount of blood that leaves your heart. Venous return is a measure of how much blood comes back. Okay. All right. And so what are some factors that affect venous return? And so some factors that affect venous return are things like the pressure gradient between between the systemic circulation and the right atrium. Okay. Because remember, the right atrium is kind of the first heart chamber that the blood sees upon returning to your heart. And so your right atrium is usually at a pretty low pressure. Okay. And so the amount of pressure gradient from your systemic circulation down to your right atrium, that's a big determinant of the venous return. Okay. The resistance of the venous vascular bed, and so that's another important factor. Okay. And so if you have a bunch of collapsed veins, and so that's going to negatively affect your venous return, because it's going to be much harder for the blood to squeeze through those collapsed veins. Okay. And another important factor are things called your calf muscle pump and the respiratory pump. Okay, which we're going to talk about on the next couple slides. But before we get there, are there any questions about venous return? That's why PDSM is not safe practice. I won't comment on that. Okay. All right. And so now let's look at what is this calf muscle pump and what are these respiratory pumps? Okay. All right, so let's talk about the calf muscle pump, and and this is not the only muscle pump that you have in your body, but it's one of the more famous ones. Okay, and it's actually the one that doctors actually target the most when they want to kind of enhance your venous flow. Okay, all right, and so the fact that we call this a pump kind of tells you that that this is kind of and almost like an assist device to kind of help the blood kind of return back to your heart. Okay. All right. And so, the kind of the main motivation for this is, because the veins are so far from your heart, right? And so, relatively speaking, the heart, after the heart pumps blood out, it first passes through all your arteries, and then it passes through your capillaries, or the microcirculation, okay? And so your veins are last. And so your veins actually feel very little influence from the heart, okay? And so in order to get blood back to your heart from the veins, they actually need a little bit of help from the rest of your body, okay? And in particular, they actually get a lot of help from your muscles, right? And so one such muscular pump is in your calf. And so actually, if you look at your calf, there's actually a gigantic vein that actually runs through your calf that you can kind of see in this figure here, okay? And what happens is when you flex your calf, and so when you kind of flex that calf muscle, what you're going to do is you're going to squeeze the vein, kind of like what we talked about before with vein collapse. But this is actually a good thing. And so, when you squeeze this calf muscle, what it's going to do is it's going to squeeze your blood up the vein and back towards the heart. Okay. Right. And so that's good. And so, your veins are actually assisted a lot by these muscle pumps, or like as you flex your muscles, a lot of times what that does is it squeezes the veins. And then as in squeezing the veins, that helps push the blood, kind of squeezes the blood back towards your heart, right? It's almost like squeezing like a ketchup packet, right? And so you squeeze the ketchup packet, and then ketchup comes out, right? And so your muscle pumps kind of do the same thing. So it's kind of squeezing your veins just to make sure that the blood goes back towards your heart. Okay. Okay. All right. Oh, question. So your calves are like two mini hearts. Yeah, kind of like that. I mean, it's not nearly as effective as your heart itself, but if you're kind of flexing your calves a lot, and this kind of naturally happens as you're walking, then that kind of helps to assist kind of blood to go back. Okay, and so that's kind of what they say. And you hear this all the time. When people talk about ergonomics or exercise or things like that, right? And so when people say that you should take a walk to get the blood circulating your body, right? What they actually mean is that, they actually want you to kind of flex your muscles a little bit to kind of, get these kind of muscle pumps in action to kind of, help your veins kind of push the blood back to your heart, right? So like as you can imagine, like if you go for a walk, like around your neighborhood, you're going to flex a lot of the muscles in your legs in order to do that. And then by doing that, you're kind of helping your veins kind of push the blood back towards your heart. Talk about good design. Yeah, actually, it's amazing. The human body is and I've talked about this with some people in this class too. The human body is, I think, the most the best designed piece of engineering that we have, right? And so it's amazing just how many systems work together in your body, and it just works, right? And so something like your muscles, right? And it's assisting your cardiovascular system, which is crazy. And the fact that this is kind of just baked in naturally is crazy. All right, question: Can it burst? No. So actually, your veins, remember, are very flexible, and so naturally they just like to collapse all the time. And and you can kind of think of them as kind of like a rubber band, right? And so your veins are going to collapse, and it's going to come back the way it was. And so no matter how buff you are, you can't flex your biceps enough. You can't go to the gun show enough such that you bust your veins, right? Because your veins are just very, very flexible, and so they're kind of just designed to handle those things. Actually, I went on a hike with my friends this weekend, and for some reason they were obsessed with this phrase because it got sunny on us and it started getting hot, and so they kept saying "sun's out, guns out," and so they started flexing like that. And it was funny the first time, but it started to get kind of annoying after that. But yeah, no matter how big your guns are, you can't break your veins. And another thing that kind of helps with these pumps is that you have these kind of tiny little valves here. And so you can kind of see this in this image here, okay? Because kind of what the fear is if you squeeze your veins and kind of push blood up, then what you're worried about is that when your muscle relaxes and your vein kind of comes back, then you're scared that the blood will just be pulled right back towards where it was before, right? And so to kind of prevent that from happening, you have these valves that just naturally appear in your veins, so that once your muscle kind of squeezes the blood forward and it passes a certain point, then it can't come back, right? And so basically, your muscle is going to flex, it's going to push the blood up, the valve is going to close, then the blood can't come back when your muscle relaxes. Right? And actually, some medical devices have actually been designed around this idea too. And so to help kind of some patients with their venous circulation, some medical devices have been designed to kind of squeeze these calves to kind of mimic these patients, mimic this this behavior. And this is specifically to help patients, after surgery who aren't able to walk. Yeah. I'm going to start working on my calves. Yeah. So if I have a heart attack, I should flex my calves to bring me back. So heart attack is something different. So heart attack is blood in your heart is being clogged, and so no matter how much you're flexing your calves, you're not going to help your heart attack. Yeah. Yeah. So heart attack is something different. Usually a part of your heart muscle is dying when you have a heart attack. Some calf raises during class. Yeah, you should do it. Yeah, I mean, any excuse that you have to go exercise, I think is good, especially, once we're indoors like this. And speaking of which, I need to start and getting back into exercising as well, because I'm definitely getting out of shape. I looked at the pictures of myself from my hike. I'm like, oh wow, I have a real pot belly now. I need to work on that after the semester's done. Okay. All right. And so that's the calf muscle pump, but that's not the only muscle pump in your body. And so, basically, most of your muscles can act as the same ones. But another big pump that occurs is the respiratory pump. Okay? So actually your diaphragm is actually another big muscle that kind of helps aid with this mechanic as well. Okay. And so the respiratory pump is actually triggered whenever you breathe, right? And so whenever you breathe, it changes the pressure inside your chest and your abdomen, which affects, the vena cava. Where your vena cava, remember these are the biggest veins in your body. Okay. And so because of this change in pressure, that again produces this kind of squeezing motion that kind of pushes, that kind of squeezes the blood in your vena cava, that pushes it towards the heart. Okay. And this effect, as you can imagine, is enhanced during exercise, because as you can imagine, when you're exercising, you're breathing a lot faster. You're like, right? So you're breathing faster and you're breathing a lot harder, right? And so the more you breathe and the harder your breaths are, it's going to enhance this respiratory pump too. Okay. And that's generally what you want when you're exercising too, because when you're exercising, your muscles are demanding a lot more oxygen, right? And so you need to circulate your blood. It needs to circulate a lot faster in your body. Okay. And so, you're breathing a lot faster, mainly to take in more oxygen into your body. But by breathing faster, you're also enhancing the blood flow that's coming to your heart, through this respiratory pump. Right? And so going back to Michael's comment earlier, so this is just kind of beautiful design where, you have one thing that's happening and it's also kind of assisting, all other parts of your body. So, beautiful, if you're a design freak, and you look at how the human body is designed and just how all these things definitely work together. It's amazing. Man. Evolution is an amazing thing. All right. Any questions on this so far? All right, question. So how do hiccups affect this pump? That's a great question. A great question that I don't know the answer to. So that's something I would need to look up. So I would imagine it would definitely affect this respiratory pump, because hiccups are kind of like involuntary kind of spasms of kind of your diaphragm muscles. But how it affects the respiratory pump, I'm actually not sure. Yeah. Okay, so let's go ahead and move on. And so let's talk a bit more about the venous valves. And so I kind of mentioned this kind of briefly in the calf muscle pump, but your veins are actually seated by a bunch of these like tiny little valves. Right? And so we've talked about valves before, not really in much detail in this class, but if you kind of remember, your heart has a bunch of these valves in it. Oops. And the main purpose of these valves is to make sure that the blood only goes in one direction, right? And so if you think about your heart,
Professor, we can't hear you. The sound just cut off.
Oh, can you hear me now? Hello?
Yes.
Okay. Yeah, my mic kind of became unplugged a little bit halfway, and so I tried to plug it back in, but I guess it didn't register. But let me work with just my laptop mic for now.
Okay, cool.
Yeah. Thanks for letting me know. Right. So venous valves, and so the purpose of these valves is just to make sure that the blood goes in one direction, because and this is kind of to work in tandem with all the pumps in your venous system, right? Because when you pump, because the thing with pumps is that your pumps can squeeze, but eventually the pumps have to relax, right? And so when the pumps relax, the danger of what can happen is that the blood can kind of get sucked back into the pump, right? And so you can imagine, you have this tube filled with fluid, right? And you can do this with like I think probably the best thing would probably be like one of those fun balloons that people tie into like funny shapes, right? And so you have kind of a long tube of air, right? You can squeeze that tube and it's going to cause air to go upwards, right? But as soon as you let go, then all the air that you squeezed up there is just going to be sucked back into the section that you had before, right? And so you don't want that in your venous system. And so in your venous system, you want it to be such that you pump blood with your calves or something, and then the blood only goes one direction. But then when your calves relax, you don't want that blood to come back. Okay, and the valves are there to basically prevent that from happening. Okay, and so that's kind of a long way to say that a valve basically kind of serves the same purpose as as a mechanical valve, where we want to prevent backflow and we want to make sure the blood only goes in one direction. And so what's unique about these venous valves is that there's actually a lot of them, and so there's actually too many to name. And so in your heart, you have 4 very distinct valves, and so they all have a name. But for the venous valves, there's so many of them that they don't really have names. We just call them all venous valves, right? And because as you can imagine, we need a lot of these valves to kind of help with the venous system, just to make sure that the blood gets back to your heart. Okay. And so let's talk about the geometry of this venous valves a little bit, okay? And so if you think about the geometry for your heart valves, it's very similar to that, okay? And kind of the most prominent characteristics here are the leaflets and the sinus, right? And so the leaflets, if you kind of remember when we talked about valves, are these kind of flexible structures that kind of open and close like this, okay? And they're flexible, as you can imagine, like a leaf would be, okay? And they're flexible in that they can open up really easily, but when they shut, they shut completely, such that they don't allow flow to come back. Okay. And so what's unique about the venous valves is that they're bicuspid, and so what that means is that there's only 2 valve leaflets. Okay. And so this is actually something I can simulate with my hand. Okay. So if you kind of see my hand from the camera, you can see here that the valve leaflets will open up like this, and then they'll close kind of like that. Okay. And so that's different from the valves in your heart, where the valves in your heart, you have the tricuspid valve, which has 3 leaflets. You have your aortic valve and your pulmonary valve, which is a 4 leaflet valve, and then you have your mitral valve, which doesn't really have leaflets. It's kind of a weird kind of void monster mouth kind of thing. Yeah, the mitral valve is like kind of a weird thing. But yeah, the mitral valve is not really a leaflet thing. But your venous valves, it actually does have leaflets that kind of open up and close, and they're actually flexible structures. Okay. All right, and so the other kind of defining characteristic for a venous valve is what's known as the valve sinus. Okay? And so in order to, this might have formed during development. I think people are kind of still studying, why these kind of things form. Whenever you have a valve like this, you kind of, right after the valve, you can have like a bulging of the artery. Okay, and so you can see here that, right after the valve leaflets here, we have this kind of bulging of the artery that looks like this. Okay? And so that's called the valve sinus. Okay? All right. And so just like I mentioned before, there's lots of these valves throughout the body, especially in your periphery veins. And so especially in the veins like in your hands, or in your legs or in your arms, right? So basically wherever you have lots of muscles, and that's far from your heart, we need to have a lot of valves in here, because as you flex those muscles, you want to make sure that the blood only goes in one direction. Okay, so any questions on this? Oh, sorry about that. Yes. Right. Yeah. No muscles, no valves. Yep. Okay. And so let's talk about some of the fluid mechanics that goes through these valves, because this is, I think, some of the more interesting fluid dynamics that you can have. Okay. And actually, if you compare that to how much the heart valves are studied, venous valves have basically not been studied at all. And so, there's really actually very, very little out there that's very little work that's out there, studying these venous valves. And part of the reason is, they're so small because your veins themselves are very small arteries, and so the valve leaflets are going to be really small, right? And so because of that, it's really hard to observe these in practice. And so people just haven't. But one thing that people have been able to determine is that, the valve leaflets, when they open, they don't go all the way to the vessel walls, right? And so what that means is that if we kind of go back to our previous figure here, okay, these valve leaflets, kind of generally what you would imagine they would do is if you kind of imagine like kind of a Western door that kind of opens like this, okay? I think, kind of the general expectation that these valve leaflets would open so much that they would kind of touch the sinus right here, okay? But that actually never happened. So actually, the venous valves, this is as big as this is as open as it would get approximately, okay? And so they actually don't open that much. And so what can happen, because the venous valves don't open fully, what that can do is it can cause kind of a local restriction of blood within the venous valve, okay? And so that basically causes the fluid velocity to increase as it's going through the valve because of that restriction, okay? Right. Okay. All right. And so before we get into posture, are there any questions on this? Okay. All right, so let's talk about how posture influences the venous flow. Okay, and so kind of the theme that's developing here is that the pressures in your veins are really, really low, right? And so we talked about that before in terms of venous collapse, right? And so because the internal pressure is so low, that causes the veins to kind of easily collapse on itself. Okay. And so another area where that low internal pressure has a big impact on the biomechanics is posture, right? And so let me just kind of remind you a little bit from your fluids class, kind of probably the very, very beginning of your fluids class, to this idea of hydrostatic pressure, right? And so hydrostatic pressure basically says that there's a pressure force that develops within a fluid based purely on height, okay? And so you can compute the hydrostatic pressure by multiplying the density of the fluid multiplied by the acceleration due to gravity, which is g, times the height, okay? And the height being the height of the fluid that's in your system, okay? And so the higher your height is, then the more hydrostatic pressure that can develop, okay? And so if you look at this figure on the right here, we have two columns, okay? And so we have one column here where the fluid is only up to a certain level. It's at kind of a low level, and we have another fluid here where the fluid obviously reaches a higher level up here. Okay, and so because the depth of this fluid is a lot higher, okay, then what happens is that near the bottom of this tank right here, you're going to have a much higher hydrostatic pressure, okay, compared to this one, because this one, the column is at a much smaller height. Okay. And so, it's a little bit subtle, but if you compare the water streams that come out of these pipes, so this is basically a leaky bucket, then what you'll see is that you have higher velocities here on the right one because you have a much higher hydrostatic pressure down here. So there's basically more force that's squeezing the liquid out of this column. Okay. All right. And so hydrostatic pressure exists in your cardiovascular system, and so your blood is not exempt from this. Okay, and so just like a column of fluid, you have hydrostatic pressure that affects your cardiovascular system. Okay, but again, for your arterial system, which is for all your arteries, most of the time we can ignore this, because if you compare kind of the relative magnitudes of like your blood pressure and the hydrostatic pressure is usually pretty low compared to the blood pressure. Okay. But for your veins, where the veins, you have much lower pressures, if you change your posture, where you change the height of a certain part of your body, that's going to affect a lot of the pressures within the veins. Okay. In other words, it's going to affect the transmural pressure. Okay. But I do want to mention that these pressure changes don't happen right away, and so if you raise your hand like this, the difference in hydrostatic pressure is not going to affect you right away. And so it usually takes about 20 seconds for the hydrostatic pressure to kind of equilibrate under the change of posture. Okay. All right, and so on the next slide, let's see. So on the next slide, I have some 3 images for you. Okay. And so you can see here that, as you can imagine, as you change your posture, or as you change kind of the height of certain parts of your body, that's going to affect the transmural pressure inside your veins. Okay? And so I have 3 different images here. And so in the first image, I basically have an image of the veins here when your hand is below your heart. Okay. And so when your hand is below your heart, that's kind of like the lowest part that or the lowest height that your hand can be. And so the hydrostatic pressure in that case is relatively high because it's lower, right? And so because the hydrostatic pressure inside the vein is relatively high, that kind of pushes the vein out, where you have these kind of nice, healthy looking veins. Okay. But if you start to raise your hand, and so in image B right here, this is an image of the vein inside your hand, where if your hand was at the level of your heart. Okay. And so you can see here we've raised the your hand up to a slightly higher height, and so the hydrostatic pressure there is going to decrease, right? Because you're raising your hand up to a higher one, and since the internal pressure inside the veins is lower, that's going to cause more of the vein to collapse, because now the external pressure is much higher compared relative to the internal one. Okay. And if we look at kind of the last image right here, where if you raise your hand all the way up as high as you can go, okay, then that's gonna cause the hydrostatic pressure in your hand to be at a minimum, right? Because you're raising it to a much higher height. Okay. And so since the hydrostatic pressure is at a minimum when you raise your hand up to the highest, then it's going to cause your veins to collapse, because then you have much less internal pressure inside your hand, and then the external pressure is going to start to dominate. It's going to cause your veins to collapse. And so, that's why, when you raise your hands for kind of a long time, you start to feel kind of a little bit of a tingling in your hands, because, the hydrostatic pressure is changing for that, right? And if you've ever injured yourself, like you've had like an ankle sprain or something playing a sport, what they always tell you is that, you should always elevate your limb relative to your heart, right? So actually, my nurse back in high school, I used to sprain my ankles a lot. So I have like ankles made of glass. And so he would always tell me, I have to incorporate RICE. And so RICE stands for rest, ice, compress, and elevate. Okay? And so the elevation part's important, because you want to encourage kind of blood flow coming back to your heart. And so you want to kind of encourage this kind of calf muscle pump. And so that's kind of why, you have to elevate, to encourage that kind of blood flow. Okay. Okay. So any questions on this? Nice. Yeah. 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 It's definitely a cool thing. Yeah. Yeah. Veins are interesting, because it's it's not often studied, but you see a lot of cool things that you kind of see in everyday life. You sprained your ankle doing a backflip. Dang. Yeah, backflip is something that is beyond me. I think if I tried to do a backflip, I think I might sprain my face instead of my ankle, because I'm not athletic at all. So the fact that you did a backflip and you kind of semi landed on your feet is pretty impressive. Yeah. Okay. And so that's how posture influences your vein flow. Okay. And so now let's talk just kind of very briefly about some venous diseases. Okay. And so, there's not much to talk about here, because there's not much diseases that are out there, but there are some that you should know. Okay. And so the first vein disease that we're going to talk about is called venous insufficiency. Okay. And so venous insufficiency has to do with venous return. You were drunk. Okay. Yeah. And so if you remember, venous return is a parameter that we use to quantify the amount of blood that returns to your heart. Okay. And so this has to be maintained at a certain level, in order for your heart to work properly. Okay. And so under the condition where you have kind of poor venous return, where not that much blood is returning to your heart, okay, then we call this venous insufficiency. Okay. And so a lot of times this this occurs in your limbs. Okay. So mostly in your legs. And so that's what you can see here in this figure. Okay. And so normally what this is caused by is abnormally higher pressure in your lower limbs. Okay. And so, that causes, and so if you have elevated pressure in your lower limbs, that kind of forms kind of like a blockage where it makes it kind of hard for blood to return from your lower limbs. Okay. And so some symptoms that you can see for venous insufficiency is you might see some dark and leathery skin. You might see like a varicose vein or two, right? So you might feel some pain or heaviness. You might see a lot of leg cramps, itchy skin, restless leg, okay? And so all of these things could be symptoms of venous insufficiency, right? And so the interesting thing, and this will be kind of a theme for all the vein diseases, is that the underlying causes are right now a little bit difficult to assess, right? Because the veins are just, relatively speaking, just very poorly studied compared to arteries, okay? And so some complications where if you have venous insufficiencies, you could have some ulcers that form, right? You might have edema, which is basically defined as you might have fluid retention in your limbs, and so you might have some swollen limbs that look like this. Okay. Or in the worst cases, you might have some fibrosis, which is basically the formation of scar tissue inside your veins. Okay. And so the primary ways of diagnosing venous insufficiency is ultrasound. Okay. And so that's one way that they can do things, okay? Because with ultrasound, what they can do is they can detect things like a lack of valves. They can see maybe there's a blockage or something, or maybe some other anatomical impediments to venous flow in your lower limbs. Okay. All right, question. So can that happen during my sleep when my leg randomly cramps at 3 a.m.? I'm not sure, actually. That's a good question. I mean, I would imagine that venous insufficiency can kind of happen at any time, and so that might be one of the causes that causes those things. But I think it kind of depends on the situation, because I think cramps can have a lot of other causes as well. Yeah. So usually after you go running, I see. Yeah, it could be. It could be one of those causes. So yeah, it might be something that you discuss with your doctor and see if that's something that they can look at. Okay, so any questions on any other questions on venous insufficiency? Okay. All right, so now let's talk about varicose veins. So I think this is the one that this is generally the vein disease that people typically hear about, okay? Because it's kind of the most visible, right? And so varicose veins they're characterized by these kind of swollen, twisted veins that you can actually see from the skin, right? And so they mostly occur in the legs. And so, I wanted to put this image here because I didn't want to put any gross images of real varicose veins. But you can easily Google this and you can kind of see what's going on. But and so it's not appealing, right? And so usually people are not happy when they get varicose veins, and they try to undergo some cosmetic procedures to kind of get rid of them, right? And so the interesting thing, just like venous insufficiency, is that the cause for varicose veins is poorly understood. Okay. And so it could be that it's you could have some valve failure that occurs in your veins, and so I think that's one thing that people have kind of correlated with this. And so if you have valve failure, then this could lead to kind of an expansion of your vein vessel walls and can cause it to kind of distort like that. Okay. Another thing that people have people have kind of done in simulations actually is that what they've kind of shown that if you have a change in the material composition of the vein wall. And so one example could be you might have increased collagen concentration, that this could be, a cause for varicose veins as well, right? And so people have basically shown in simulations that if you have increased collagen concentration, that it can lead to kind of these varicose vein shapes, right? The only problem is that, we don't know exactly, like we know that, increased collagen could be a cause for varicose veins. But why, the collagen concentration would be increasing in patients with varicose veins is not not known, right? And so there's still kind of a ways to go in order to understand, what's exactly going on with varicose veins. Right? All right. So any questions on varicose veins? Okay. All right. And so the last vein disease that I want to go over is deep vein thrombosis, or DVT. Okay. And so the key word here is thrombosis. Okay. And so thrombosis is just another fancy word for blood clot. Okay. And so a deep vein thrombosis, as you can kind of infer from the name, is just a blood clot that occurs in your deep veins. Okay? And so your deep veins are basically the veins that are in your legs. Okay. And so the scary thing about this, just like kind of most blood clots, is that they're asymptomatic, right? And so most people don't even realize that they have a blood clot. Okay. Because a lot of times, the blood clot itself doesn't fully constrict the vessel, right? And so you could have a blood clot that occurs like this image right here, where it only kind of partially, occludes or partially blocks the vein. Okay. And so you can still have blood flow through this, but you kind of have this big kind of thing that's forming on the side of your blood vessel, which is not good. Okay. And so by themselves, actually, they're actually not that bad. And so, if you have a thrombosis in your vein, usually it's not the end of the world, because there's a lot of veins out there, and you have one that's blocked up. You might get some symptoms, like you might have, discoloring of the skin, or swelling of the legs, but ultimately it's not that big a deal, because you have other veins that kind of lead back to your heart. Okay. Actually, the most severe thing that can happen is if the thrombus or the clot actually detaches from the wall and actually goes to somewhere else in your body. Okay. And this is kind of the danger for blood clots anywhere in your body, where a lot of times, the places where blood clots form, usually it's not that big a deal. But the fear is that, if the blood clot detaches and it goes back into your heart, and if it clogs like an important channel in your heart, that's when things start to get really bad. Okay. And so, these are the kinds of things that cause heart attacks, or if you have kind of a thrombosis that forms, or a blood clot that forms in kind of the key area in your heart, and your heart's not able to get, the oxygen and nutrients that it needs, that's what causes heart attacks, right? And this is typically what causes strokes too. So if you have a blood clot that forms in one part of your body and it flows up to your brain and kind of gets stuck in your brain, and suddenly your brain's not able to get, the blood that it needs, that's what causes strokes. Okay. And so this is the worst fear with thrombosis or blood clots, is that, that not only do they form, but that they detach and go somewhere else in your body. Okay. Okay. And so just like the other two vein diseases, deep vein thrombosis, relatively, poorly understood, but, from post-mortem studies, or for, when people cut open cadavers, what people have found is that, generally these thrombus or these blood clots tend to form around the location of the veins. Okay. And so that's what you see in this image here. Okay. And this kind of makes sense, because the veins are kind of this thing that kind of blocks flow and kind of opens like this. Okay. And so in order for the blood to kind of go around the vein, it kind of has to strike the vein and kind of go around it. Okay. And then as the blood kind of exits the vein, you might have these kind of weird recirculation zones. Okay. And it's already been shown that in other parts of the body, that these kind of flow characteristics, where you have kind of blood that's impinging on a certain surface and blood that's recirculating, these are kind of the characteristics that cause blood clots. And so that kind of makes sense, kind of based on what we understand from other parts of the body. Okay. Okay. And so one thing that can increase your risk of deep vein thrombosis is long periods of inactivity. So speaking of the pandemic, right? And so, during if you're kind of just sit on your butt all day, then your skeletal muscles aren't really doing much, right? And so if your skeletal muscles aren't really doing the pumping that it needs to do, then your blood can kind of stagnate inside your veins quite a bit. Okay. And blood stagnation is another thing that's been known to cause blood clots in other parts. Okay. And so this is another important reason that you want to exercise this, because you want to stimulate your muscles. You want to stimulate those muscle pumps so that you kind of help kind of encourage the blood flow in your body, so that you kind of decrease your risk of blood clots like this. Okay. All right. So any final questions before we wrap up for today? All right. So any cures for that? Yeah, it's so if you want to prevent blood clots, there's a medicine that you can take called blood thinners. And so that's basically a anticoagulation therapy And so that's kind of the formal name for blood thinners. And so what anticoagulation will do is that it'll inhibit kind of the chemical response in your body that causes blood clotting. And so if you inhibit that kind of chemical response, then your blood will clot a lot less. Yeah. And so you have to be careful for that. And so if you're going to take some blood thinners, what that means is that your blood won't be able to clot in other parts where it needs to clot, right? And so and so kind of the most common place where you need a blood clot is if you cut yourself, right? Because when you kind of pierce your skin, the blood needs to clot around your wound in order for your skin to heal, right? And so if you're taking blood thinners, kind of the joke that a lot of cardiologists say is that okay, you're on blood thinners now, so don't go out and scrape your knee, otherwise you might bleed to death. And so it's just a joke, but it's true. Where if you have a significant wound when you're on blood thinners, then your blood won't be able to clot, and you'll literally just the blood will just keep coming out, and there's nothing that's there that's going to stop it. And so you really need to be careful if you're on blood thinners. Right? All right, question. So isn't thrombosis the disease linked with the Johnson & Johnson vaccine? Yes. So if you kind of been keeping up with current events, the Johnson & Johnson vaccine was paused because it caused blood clots in 6 women, I believe. And so I think they put it on pause so that they can understand it a bit more. I don't know if they kind of tracked down kind of the exact reason why it was causing blood clots, but yeah, it's a big deal, because if a blood clot forms in the wrong part of your body, that's a bad thing. I think one of those women actually died because I think she had a blood clot either happened in her heart or in her brain or something like that. Yeah. All right, question. So once you have a blood clot and then exercise, isn't there a greater chance that the blood clot can move? Yes, that is true. But you also increase the chance that the blood clot might also kind of break up on its own as well. Yeah. And so it's that's usually kind of the thing that you're hoping for. Yeah. Right. Yeah. So they are. I think what I read is that they're bringing back the Johnson & Johnson vaccine, but I think with a warning. So it sounds like they didn't get to the root cause. Which would be surprising to me if they found that out so quickly. But I think they're putting it back in production with the warning that said you might get blood clots from this. So not the best thing, but at the same time, the incidence rate was very low for that blood clotting. But it's good that they paused it at least, and I'm sure that they're taking a lot of time now to find out what's happening. Yeah. And yeah, the COVID outbreak in India is really scary right now. Yeah. Yes, actually, yeah. So actually, Michael, that's a great point. So one of the points that the textbook makes is that if you're on long flights, that actually is a risk for deep vein thrombosis too. And so definitely when you're on a long flight like that, definitely get up, go to the bathroom, walk around a bit, because you want to stimulate your muscles to kind of to encourage that. Yeah. So I think taking aspirin can help to move it. Yes, aspirin definitely does help with that as well. Mm-hmm. All right, and so we're is aspirin a blood thinner? I'm actually not sure. Aspirin's not a blood thinner, because usually you have to be prescribed that from a doctor. But I'm actually not exactly sure what aspirin actually does. But I know it does help with a lot of cardiovascular functions. But I don't think it's a blood thinner. I think it does other stuff. Yeah. All right. So I'm going to end a little bit early today because it's a little bit too short of a time to move on to the next set of lecture notes. And so I'll stick around to chat for a while just because we have some time, and I think people are interested in discussing some stuff. But if you have some other place to be, definitely I'm not going to keep you. So thank you guys for tuning in today. Check out the study guide for the midterm, and so definitely go down that list and see what topics are good for you and what topics that you want me to review. Okay. And so have a great evening, everyone, and I'll see everyone on Thursday. Can alcohol work as a blood thinner? Alcohol is not a blood thinner. It does other stuff to your blood, but it's not a blood thinner. Yeah. All right, thanks. Have a good day too. Don't drink too much. It's a Tuesday. You can drink more on Thursdays and Fridays.
Have a good night, Professor.
Thanks. You too.